we continue our discussion of congruences. Let me record one famous theorem about congruences, and that one we'll use for some cryptography at the end of the section. So it says the following, theorem 645. It says the following: let P and Q be two distinct prime numbers. And let A be an integer. A not divisible, P does not divide A, and Q does not divide A. Then we have the following: A to the P minus 1 is congruent with 1 modulo P. And the second one, A to the P minus 1, Q minus 1 is congruent with 1 modulo PQ. The top one is the famous Fermat's theorem, little Fermat's theorem. This is little. Little Fermat's theorem, because there is a big one that was famous, long-standing open problem. So, and that's why people call this one little one, although this one is important theorem with lots of applications. So generally, before I do the proof, let me illustrate what is this telling us. So for example, if I need to calculate 7 to 260, and if I want 7, no, this is not a prime, I'll have to change that. 7 to, let's say, 42. And if I want it modulo 43, I have no dilemmas. 7 to the 42 is congruent with 1 modulo 43. Why? Because 43 is a prime, here is 42, and 7 is not divisible by 43. So it all matches, so little Fermat's theorem says remainder is 1. What is the idea of the proof? The idea says the following. Let me look at the numbers a times 1, a times 2, up to a times p minus 1. These numbers, and that's not maybe obvious, but it's fairly easy to prove, that each of them is congruent with the different numbers. So it's congruent with some number I1, congruent with I2, congruent with IP minus 1. I don't know what they are, but I know that they are not congruent. So basically these numbers, I don't know in which order, are basically again 1, 2, 3 to pi p minus 1. I don't know which one of them is 1, but since they are not congruent among themselves, then they are different, they have different remainders modulo p. And then what if I multiply modulo p? If I multiply left and right side, what happens? I get a to the p minus 1, because a is repeated p minus 1 times 1 times 2 times p minus 1 is congruent. Now I have I1 times I2 times I p minus 1. I don't know which one is which part, but for product it doesn't matter. They are basically product of first p minus 1 numbers. And then what happens if I cancel, and I can cancel congruencies if the number is relatively prime to the index. I'm again using another property that we didn't prove over here. We get, but it's easy to prove, a to the p minus 1 is congruent with 1 modulo p. And then part 2 is proved in a very similar way, or using the first rule. And then what? Let me show you an interesting way how we can use this property actually for the coding using primes. So, so what would that be? So cryptography, a little bit of cryptography, really nothing that can be called serious cryptography. But cryptography what we have there is just we are transferring some sequence of symbols. Let me call these symbols C1, C2 up to Cn. And then we are afraid that that this communication might be intercepted by the enemy, and then we just use some coding function and that produces f of C1, f of C2, and f of Cn. And then what? When this message is sent through insecure channel, then someone might get that coded message, this coded message. But in order to get the original message, one needs to have an inverse for that process, and if the coding is done in a skillful way, then inverse process is not so easy to organize. Actually, inverse process is actually breaking the code. So the simple one is Caesar's cipher. So what? So for example, if we have example 643. Here what we did, we replaced letter by their rank. Now we add a fixed number. So let's say we are adding 5 modulo 26. That's what I wanted to see. So there was this tech. And tech, according to the order of these letters in the alphabet, is 20, E is 5th in the order, and X is 24. And then what simple coding would be to add 5 to each of them. So that's that coding, so we'd get +5. That's Caesar's technique, 25, 10, 29, but we added modulo 26 because there are 26 letters. So 24 and 5 will not be 29, that will be 3. So then 25, 10, 3, if you look at the 25th, 10th, and 3rd letter, we'll let YJC. So that's the coded word. So that's the word that's sent, and then of course, any serious hacker would break that easily. But if we want to recover the word, then we would need to invert the procedure. So recognize them as 25th, 10th, and 3rd, subtract 5, and then get the word 10. There's a whole theory about it, how to choose the coding, and then how to recognize frequency of letters in the word. So that's a separate discipline, and many of you might see it in your computer science education. Here we just want to connect with congruencies, how this could be used. And then, so here's one interesting technique, and generally, before we even express the problem and how to use the coding, let me do one example that actually repeats what it did in the previous section. So I'll just record the result, example 644. Let us find, for whatever reason, I'm not explaining it now, what is the inverse of 5 modulo 72. So we want to solve the following equation, 5x congruent with 1 modulo 72, and then we explained last time we use Euclidean algorithm, and then section, or actually the same section earlier in this section. And get actually that 5 times 29 is congruent with 1 modulo 72, and then 29 is actually the inverse. 29 is the inverse of 5 modulo 72. All right, then what do we do? Let me try the black pen again. It's completely bad. Oh, there's another one. So what do we do? Now it is the following. Suppose, so here is the idea of the coding. Idea of coding. We use module 95. Why that one? You can, for any practical purposes, you use a much bigger number. This is just for illustration purposes. The whole idea is that it's product of two primes. 5 times 19, both primes. Okay. And then what? The idea is the following one. According to the theorem that we saw a minute ago, if P does not divide A, and Q does not divide A to the P minus 1, Q minus 1 will be congruent to 1 modulo PQ. In this case, P and Q are 5 and 19, we'll get that A to 4 times 18, 5 minus 1, 19 minus 1, is congruent with 1 modulo 95. So generally it tells us that A to the 72 is congruent with 1 modulo 95. That's why in this previous example I solved this problem on of inverse modulo 72. So how will all that play? So here's the coding procedure. So here's example. Someone coded a secret digit. A digit A between 1 and 94 by raising it to the 5th power. So that person did A to the 5th, reduced modulo 95 like we did in Caesar cipher, and got the result 27. So 27 is coded the version of A. My question is, can we break the code? Can we recover A? So generally what? You can say the following. Oh, if I were able to take a 5th root, but there's no 5th root among the integers. But instead of going down, we actually want to go up. We'll say the following. Let me try, because I cannot go backwards. Let me try to raise both sides to some k, which I don't know what is it. So that actually that 5 gets erased. That's surprising in calculus or in real numbers, in integers, but actually modulo calculation it's not. Why? Because here it is. Look at this. Let us choose k such that 5k is congruent with 1 modulo 72. And you will see in a moment why. By the way, I already prepared for that, which means, according to the previous example, k equals 29. Why is 29 the key? 29 is really playing like a role of the 5th root. Why? Because here it is. A to the 5th to the 29 is congruent with 2 to the 29 modulo 95. But then what happens? So it looks even worse. Here it says 5 times 29. So instead of getting lower power, I got higher power. But generally what? 5 times 29 is congruent. It says 5 times 29 is congruent with 1 modulo 72. That means that 5 times 29 equals 72q plus 1. So this will be 8, I don't care how much is that q. And that's what? 8 to the 72q times 8 to the 1. 8 to the 72q is 8 to the 72 to the q times 8 to the 1. But 8 to the 72 is 1, that's why I wanted multiples of 72. So this is just 1 to the q times 8 to the 1, and just congruent with A. So generally multiplying by 29 creates a few 72s, I don't care about them because they produce one modulo 95, this is all modulo 95. And they actually erase that extra power and give me back power 1, and that's what we want. So this is the recovery. So solution is A is congruent with what? Because this gives me just A. With 2 to the 29 modulo 95. And then with the way we explained earlier today, how do we calculate the powers? We not 2, sorry, this is 27, I read this wrong. 27, just so 2, so 27, 29. And that's what's left, is to calculate how much is 27 to the 29 modulo 95, and I will finish it here because I have no space. So let me erase this, and all this. So generally 27 to 29, let's calculate. So A is congruent with 27 to the 29 modulo 95. So how did we do that? We say 29 powers of 2, 2 to the 4th, which is 16, plus 2 to the 3rd, which is 8. So this is what? 16, 8, 24, plus 2 squared, 24, 28, and 1. So generally, 29 to the 1 is just 29. I don't need 29 squared, because I need 29 to the 4, 8, 16, but I have to calculate it, and the way we, what's 27? 29 is fine, 27 to the 1st. I'm raising 27 to these powers. 27 to the square is congruent with 64 modulo 95. 27 to the 4th is congruent modulo 95 when I square 64 squared. And that gives me 11. 27 to the 8th is congruent with 11 squared modulo 95. That one you can calculate even by hand. That's 26. 27 to the 16th is congruent modulo 95 with 11. And then what? The same way as we did earlier today, I need 16, which is this guy. I need 8, which is this guy. I need 4th power, which is this guy, and just 27 here. So I get what? That A is congruent with 29 times 11 times 26 times another 11 modulo 95. And when you reduce it modulo 95, you get 12. 27, sorry, this is 27. 11 times 11. So 27, 29 are close, but I shouldn't mix them up. So 27 is in the base, and then 29 was broken into these powers. And then we're repeating it here. And generally, what? Of course, you can test this result, so test it. So if you take 12 and you raise it to power 5, because that's what we decoded. Someone was coded to power 5 and gave us 27. We said it's 12. If you try 12 to the 5th and you raise it modulo 95 and reduce it, you should get 27. Just to check work. So that's one nice application of this congruence theory to encryption. So once again, let me emphasize, that's probably the trickiest thing. There are two congruencies that you run. So on the ground, you run congruence modulo 95, which is PQ. But in the exponent, because you get P minus 1 times Q minus 1, which is 72, you run congruence modulo 72. So you reduce exponents modulo 72, but then because whatever's multiple of 72 will produce no effect on the base A, but then whatever's after that, the remainder after that, that will be used to finish your calculation. So modulo 72 on top in the exponent and modulo 95 on the ground.